Hello everybody. So today we're going to talk about valence shell electron pair repulsion theory and molecular geometry. And to start off, we really need to discuss what electron domains are. We are going to define electron domains as the number of things coming off of the central atom. Now it's very important to note that this is the number of different things coming off of the central atom, and these things are electrons. I figure the best way to tackle this topic is to jump right into examples. The first example I want to go over is water. So, there are 4 different things coming off of the central atom, this oxygen atom, in this water molecule. You have a pair of electrons here, 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 and here. So that adds up to 4. So this stuff really is quite intuitive. So since there's 4 different things coming off, it has 4 domains. And since we are talking about VSEPR theory right now, when it comes to the shape, this is going to be tetrahedral. Just going to go hedral. And that's because we're looking at the number of different things that are coming off of it. When it comes to molecular geometry, it is going to be a little different. The next example that I would like to go over involves this boron right here. And as you can see, you have 3 distinct things coming off of it, which means this has 3 electron domains. Now what's important is you can see there are no lone pairs of electrons coming off this boron, only 3 things. So it is actually a planar molecule, and it's called Trigonal Planar. So I'm just going to abbreviate it as Trig. Planar. The next molecule that I would like to talk about is carbon dioxide. So, go ahead and test your knowledge right now and see if you can figure out how many electron domains come off of this central carbon. Now, if you said 4, you would be incorrect, because we need to look at things coming off the central carbon in different directions. So that means we have these double bonds here and this pair of double bonds here. So you would have 2 electron domains. And can you think of what angle this would take on? Well, it's linear, and they would say it's 180 degrees, which brings me to a good point, which I missed in the previous 2 examples. So when it comes to the 4 domains, this example right here, the angle that this tetrahedral shape takes on is, do you have a guess? It's 109.5 degrees. Now, it's really important to note the reason for this, which I'll go into depth a little later on, or maybe in another video, is because when you have the 4 things bonded to the central atom, it is not planar. And I won't get into the theory of it because there's really no need for a test like this, because they're not going to test your knowledge. But when you draw a tetrahedral molecule, here's your central carbon. You have an H coming off of it. Here, this dash represents that the H is from behind. This wedge represents that this H is coming out in front of you. And then here's the other one. So it's important to note that this angle between these 2 molecules is 109.5 degrees. Now for our trigonal planar molecule that we had previously, it's important to note that the angles are 120 degrees, and this is because they all have to add up to 360, and they are planar. So it's just an important thing to note. Now, it's important to know that it is possible to have more than 4 domains. You could have 5 domains, and this would be called Trigonal Bi-Pyramidal. And it's less likely to pop up on your test, but it's still good to know because it could pop up on your test, and the angles that make up this one in particular are 90 degrees between bonds, 120 degrees, as well as 180 degrees. I know it's not fun, but it's something that you should have memorized before you walk in on test day. And you're going to dislike me for this, but you could also have 6 domains, but I think it's a little more simple than the 5 domains because they call it octahedral, and the angles are all represented by 90 degrees. Getting into the molecular geometry of things, let's start off with an example. So, a molecule like NH3 has a lone pair of electrons. And this is going to be different from the electron domains and the VSEPR theory. So these electrons are going to push these bonds down like this, and is going to end up giving a molecular angle, which I'm going to write right here, molecular geometry, of about 107 degrees, which is smaller than that of the electron domain. And instead of being tetrahedral as it would be in the electron domain, this is called Trigonal Pyramidal. Next, let's go ahead and look at the example of water. So as you can see here, if we were looking at electron domains, there would be 4 different things coming off of this molecule. We would call it tetrahedral, but that's not what we're looking at here. We're looking at the molecular geometry. And because these electrons here are going to bend this water molecule like that, it is going to have angles of 104.5 degrees. Now that's not exact, it's about there. And can you guess what it's called? Bent. So that's pretty easy to remember, and it should cause you any issues. Next, let's go over an example of something that has 5 electron domains coming off of it. So let me just go ahead and write this in really quickly here. And then you have your lone pair there. So if we're looking at electron domains, this would have 5, but again, that's not what we're doing. We're looking at the molecular geometry of it. So, do you have any idea what this would be called? We would call this seesaw. And this is much more unlikely to pop up on your test, but it's something important to know just in case you get hit with it on test day. An important side note is that when you have a molecule that lacks a lone pair of electrons, that the molecular geometry as well as the electron domain geometry are going to have the same shape. An example of this would be carbon dioxide, which is linear and 180 degrees. And that finishes up this video. Good luck with everything, guys.